Hello friends, today we'll find the kinetic energy, speed of alpha particle emitted in alpha decay. So this is a concept of collision. This is before decay, this is after decay. This is a parent nucleus, daughter nucleus, alpha particle, and Q energy released. Okay, so we'll apply the law of conservation of linear momentum. Okay, so apply the law of conservation of linear momentum. Law of conservation of linear momentum. Okay, law of conservation of linear momentum. So md vd plus m alpha v alpha is equal to 0. So we need to add the momentum of daughter nucleus and momentum of alpha particle, that is a helium. So momentum of helium, momentum of daughter nucleus. Now what we'll do, we'll need to find the Vd. Why? Because we will substitute in the further equation. So Vd is equal to minus m alpha v alpha divided by md. Okay, so let it as equation 1. Okay, to take as equation 1. Now move to the another page. So what we had from the previous page is like Vd equal to minus m alpha which is not clear due to it's not being visible, not visible. Okay, look once again. Okay, now what we got from the previous page is m alpha v alpha md, equation 1. Okay, this is what we got from the previous page. Now apply the law of conservation of energy. Law of conservation of energy. So apply, which is the kinetic energy. So same like first of all we have to add the two kinetic energy of daughter nucleus and alpha particle. So md vd square, kinetic energy of daughter nucleus, and this is kinetic energy of alpha daughter nucleus. This is the kinetic energy of alpha nucleus is equal to Q, the energy released. Okay, now what we'll do, we'll substitute the equation 1 in Vd. Okay, in equation this is equation 2, so substitute the equation 1 in equation 2. What we'll do, we'll substitute the Vd here. So let's substitute. So m alpha v alpha by md square plus half m alpha v alpha square is equal to Q. Okay, so what we'll do, so just we have to take the square. Okay, md equal to m alpha square v alpha square by md square is equal to, right as it is, of another term. So what we'll do, this 1 md will cancel here, and we're left with, now take a common. Okay, now take common, like half m alpha v alpha square will be common. Half m alpha v alpha square will be the common. So we're left with m alpha here divided by md plus 1 equal to Q. Now what we'll do, we can term this as a kinetic energy of alpha, Ke alpha. Okay, Ke alpha. So this is Ke alpha, and what we'll do, now we'll put like here, come here, like m alpha equal to the mass of alpha particle, that is the mass of helium. We know the mass of helium. Mass of helium is 4. Okay, so 4 its unit is AMU. So MD, what is the mass of daughter nucleus? To come to the beginning page, the mass of daughter nucleus is A minus 4. Okay, A minus 4. So write A minus 4 here, and now put the value M alpha and V alpha here. So it is like 4 by A minus 4 plus 1. Okay, now simplify. So here I am simplifying. Ke, that is kinetic energy of alpha, A minus 4 A minus 4 equal to Q. So here 4 will get cancelled, and now what we'll do, so Ke, that is K of alpha, kinetic energy of alpha particle equal to Q. Take this shift this in another side, so A by 4 by A. So this is a kinetic energy. We found the kinetic energy. So we're done with the kinetic energy. Now we'll find the speed V alpha. Okay, so let's go. So what we find from the previous is like Ke alpha equal to A by 4 by A Q. Okay, so this is what we gonna find. We did find. Okay, now what we'll do, we'll write the proper form, like K alpha means what, half M alpha V alpha square is equal to A by 4 by A into Q. Okay, now what we'll do, we'll find the we will separate half M alpha from here. Okay, so this will be this. Okay, now what we'll do, V alpha take a square root. So this is our velocity of alpha particle. Okay, so this is what we'll find the velocity of alpha particle. So we're done with velocity of alpha particle. Thank you. Hello friends, today we will derive the mathematical form of decay law. So this is what we will derive. So according to decay law, now we will equate and there is a constant lambda. This constant lambda is the decay constant, which is the disintegration constant. Okay, this is the disintegration constant, and this is also called decay constant. Okay, now what we'll do, just we'll do a simple integration. So dn by n is equal to minus lambda dt. Now we'll do the integration inside. Okay, after doing the integration, we'll left with the log en equal to lambda minus lambda, and the integration of dt is t. Okay, plus k is the constant. So when we put t equal to 0, then n is equal to n naught. So log en naught equal to k. Now put the value of k in this. So log e equal to minus log e and not. Okay, now what we'll do, so this will happen log e and not minus lambda t and log n by n naught. Okay, minus lambda t. Now what we'll do, now we will take a exponential. Okay, after for taking it taking the exponential both side, then log will cancel and e to the power minus lambda t will left with. Okay, and n equal to n in this. So we'll have our equation this. Proved. Thank you. Just take a look. Okay. Hello everyone. Today we'll derive the mean life, which is actually an average life of a radioactive substance. Okay, that's what we'll derive. This is mean is equal to 1 by lambda. Okay, it's inversely proportional to the lambda, which is the decay constant, and which is the disintegration constant. Okay, constant. So this is what we'll derive. Okay, so let's go. So what is mean life? So first of all, you should know the sum of lives of all nuclei to the total number of nuclei present. Okay, this is what mean life means. Like this is T total divided by n naught. Okay, this is the total number of nuclei. N naught is the total number of nuclei. So from the mathematical law of decay, we'll have n equal to n naught e to the power minus lambda t. And when we'll differentiate, like differentiate with respect to t, differentiate. So yeah, so minus lambda comes out and we'll have this. Okay, simply how we derive is like if there is a, suppose is minus 3x, and we take the differentiation, then what will happen, minus 3 will come outside and is this. Okay, this is the kind of differentiation we're talking about. And after this, what we'll do, take dt in the other side. Okay, this is lambda minus n naught and e to the power minus lambda t dt. Okay, and take these, like take the mod. Okay, take the mod of dn. We'll have lambda and n naught e power minus lambda t dt. Okay, so we are moving to the next page. So T total, how we'll find the T total? So T total is equal to n to the power and not and n to the 0 to the t and dnt. Okay, and here like n equal to, when n equal to n naught t is equal to 0 and n equal to 0 t equals to infinity. So we're gonna put this. So from n equal to n, t is equal to 0, and n equal to 0, t equal to infinity. So what we'll do, take t as t, and we'll have the value like dn, like we have the value dn, so we'll put this value here. So this is the lambda n naught e to the power minus lambda t dt. There is only thing one left, which is the integration. Okay, so this is the common term. First of all, take out the common term from the integration. Lambda and n naught is the common term. It is the so simple integration. Okay, integration by parts. We will do the integration by parts. And there is also t. That's why we're gonna do the integration by parts. Let's do the integration by parts of these. Okay, so let's go. So here is like infinity to t minus lambda t dt. We'll simply doing the integration by parts. Okay, this is what we'll doing the integration by parts. So here is like lambda t minus lambda out is like 1 minus lambda will be out. There is dt. So like t lambda minus t minus so is like plus lambda square and okay, this is what we'll have. So we'll take it as now we know this is like infinity to 0 to infinity, and this will become the 0. Okay, this will become the 0. Why? Because if you multiply 0 with 0, we'll have the 0, and it is t now, that's why. Okay, now simply we're doing like infinity minus infinity to the minus 0. So here is the case, like if we have the minus infinity to the exponential power minus infinity, then we'll have the 0, and if exponential is power 0, then it will be the 1. So here is like 0 minus 1 by lambda square. It is visible to all of you, and that will be lambda square minus 1. So it will be minus lambda square. Okay, so we'll have the integration. Now we'll put the integration value here. So will be half lambda square. Okay, 1 by lambda square. Okay, so now we'll have minus lambda not by lambda. So there is a mistake I have done. So let's check the mistake, because we left with no minus negative sign. So where will mistake? Let's see. mistake where we'll mistake. Okay. If this would be the plus, okay, yeah, here will be the minus sign. Here is already the minus sign, and this is minus, because when we cancel this minus, we will have the plus sign here. So after integration, this will become the minus, and this will be the minus. Okay, so minus minus, it will be the plus. So this is what I have mistaken, so sorry for this mistake. This will be the plus. Okay, this is minus. Okay, this will be the plus, sorry. Okay, so we'll have this value. Okay, that value. So here I mistake, here will be the plus sign, not minus. So thank you. Now what we'll do, we'll do the like this formula, right? So here, like T total is equal to n by lambda and n naught. So here is like 1 by lambda. We proved. Okay, what we proved is, okay, this is like proved. Thank you. Hello friends, today we're gonna derive the half-life of a radioactive substance. Okay, so we know from mathematical form of decay law, n equal to n naught e to the power minus lambda t. So this is what we know, and when we'll take t equal to half-life, means t equal to half, then it's then we'll have the n equal to and not half. Okay, for the condition if we take the t equal to time half. Okay, and now put this value, both value in there, and we'll have n naught by 2 is equal to n naught. Instead of t, we'll put the t half. Okay, and now we'll have the half equal to exponential minus lambda t half, and when we'll instead of we write the positive sign of the lambda, we'll get this. Okay, 2. Taking the exponential cancel, we have to apply the logarithm rule. So lambda t are equal to log 2. Okay, and t half equal to log e2 by lambda. Now we know that if we're taking, for example, log ex, like log ex, so is equal to the 3.303 log 10 x. Okay, so that's we gonna apply here 2.2 log yeah, 10 to base will be the 10. Okay, so that's the difference, and by lambda. So we'll take this equation from here, and t half, that is also okay, t half equal to 2 log 2. What is the value of log 2? If the base is 10, then its value is 0.3010, okay, divided by lambda. When we'll solve, it become 0.6931 lambda. Okay, so we'll got our answer. This is our answer. Okay, if you have doubt how it comes, like the value of log 10 to the power base 2 and 2 log is like equal to this. Okay, that's why we put this value here. Okay, instead of writing log 10 to is, we'll put this value. Thank you. Just take a look. Okay, thank you. Hello everyone, now we'll derive the instantaneous rate of change of the activity of a radioactive substance is inversely proportional to the square of its half-life. Okay, so what we're going to derive is d by rt is proportional to 1 by half-life square. Okay, this is the thing we are gonna derive. Okay, so before deriving this equation, we should know this equation of radioactivity. Okay, and after getting it, we need to differentiate with respect to the time. So while we are differentiating with respect to time, lambda comes out RE. Okay, and this whole term will become R. Okay, the activity of the substance, and then it become R. It is dr by dt. We also know the activity is lambda n. Now put this value here, so it will become lambda n. So lambda square n dr by dt. So we know that the lambda is equal to 6.6931 by half-life. So here we will put all this 31 square n and r. So we can also now just we have gotten the square here. So clearly we can say dr by dt is proportional to the 1 by half-life square. Okay, and this is proved. Check. Hello everyone, today we will know how to calculate the age of a fossil using carbon dating. Okay, so we should know the formula first. This is R equal to R naught e to the minus power lambda t, and we'll divide with the R naught, then we'll get this, and now making it as a positive, so R naught by R, this will be the form. Okay, now we'll take the logarithm to the both sides, so lambda t equal to log e, is the base, and we'll do the time as half log e r naught by r. Okay, so we know that the lambda, which is the disintegration constant, equal to the 0.6931 by half-life. So put this value here. We'll get 0.631 half-life log r naught by r t. Okay, so we prove it. Thank you. Take a look to the entire. Hello friends, we will know how to calculate the age of a rock or an old monument using uranium dating. So if you know the equation of mathematical form of decay law, which is n equal to n naught e to the power minus lambda t, and uranium atomic mass is 238 and lead mass is 206. And what we'll do, we'll consider the formula in the form of uranium and lead, but here in lead n naught minus n of u23 will be taken. Okay, so now put the value of n u3 and n uranium 238, which is the equation 1, and now after putting it we should know the activity of a radioactive substance, which is equal to the n uranium 238 divided by n lead 206. Okay, put the equation 1 and equation 2 here to solve this problem. So and there is n naught will be considered as common, and this will be cancelled, n naught, and we're left with this equation. And now I'm turning the page, and what will got from the previous page, so is r equal to e to the power minus lambda by 1 minus e to the power minus lambda t. Okay, what we'll do, we'll divide the numerator and denominator by e absolute naught minus e absolute naught. Okay, so after dividing it, we'll get 1 by e absolute naught minus 1. So what we'll do, we will shift the r value. No, we will not shift the r value. What we'll do, we'll shift the minus 1 value here with 1 minus r's. Okay, and now what we'll do, we'll take the logarithm to the both side. After taking the logarithm with the both side, with having the e power base, so lambda t equal to log e 1 by r plus 1, and this is, we'll get the equation. This is our fundamental equation. But if you want to go further ahead, so you have to write like lambda equal to 0.6396931. Okay, by time half-life. Okay, so when you will put in the lambda, we'll get this further equation. Okay, so if you're okay with this, and this is the fundamental equation, but if you want to go further, so put this value here and you will get the proper equation. Okay, so this is it all about. Thank you for watching.